the people who considered that didn't really understand what they were talking about. They literally did not know what they were talking about, and they still don't know what they're talking about. And unfortunately, that's the reality of a lot of parts of science. Once they go off on a tangent, they start to dig in their heels and they stay there. So we have two models of H2O polarity, the traditional model and its electronegativity differences between the atoms here. So the hydrogen has a slighter electronegativity and the oxygen has a greater electronegativity, and it pulls more of the electrons down. The electrons are negative. This makes the oxygen molecule more relatively negative, and it makes these more relatively positive. Now on the other model, and this is the model I introduced, it involves electrical gradients. It says there's an electrical gradient going here. And so in 4 places we have an electrical gradient going across over a nucleus. And similar to this, the reason those electrical gradients are there is because there's kind of an electronegativity difference, but on this one, we specify the actual electrical gradients. On this one, it's just kind of generalized. And you might think, well, what's the big deal? Why does it really matter? Well, as I've explained in other videos, I don't know if you've seen those yet, but when you do draw in hydrogen bonds, these are other H2O molecules. They put in opposing electrical gradients. That opposes the electrical gradients going across this nuclei. And if we also put in hydrogen bonds right up here, there's another one right there. Now we have opposing electrical gradients coming from this direction that are opposing the gradients on the nuclei on the hydrogen. So each additional hydrogen bond, and it can be up to 4, neutralizes, bringing this from 100% polarity all the way down to 0% polarity. This is now at 0% polarity because all of its electrical gradients are contradicted. And so its net electrical gradient is 0. Now, on this one, when it makes hydrogen bonds, we have one there, we have one here. Well, nothing changes because we're not concerned with electrical gradients on this one. And so on this one, since it is according to its theory anyways, it is the molecule that determines the electronegativity difference, and that makes the polarity is static. It never changes. Whereas on this one, it changes every single time there's an additional hydrogen bond made. Here's something to consider for water. The densest form of water is the one where it has the greatest number of hydrogen bonds, is the liquid phase. Why is that? Because the liquid phase, there's a lot of connectedness, but there's a lot of very slight polarity. So there's not a lot of force to that connectedness. So these molecules, when they're like this, are just barely holding on there, if they're holding on at all. In fact, they're more likely to bounce a little bit. We have realized that the polarity of the H2O molecule is not static, but variable. The mechanism of this variability is a consequence of the fact that as hydrogen bonds form between adjacent H2O molecules, each of the H2O molecules brings electrical gradients that contribute to each other's net electrical gradients, thereby and unavoidably canceling out, neutralizing a portion up to 25% of the electrical gradients that cause the polarity in both of the H2O molecules that participate in the bond. So this is our rule for understanding the magnitude of H2O polarity. So here we have an H2O molecule, and its polarity, since it doesn't have any hydrogen bonds, it's going to be at 100% because it still has all of its electrical gradients, 4 electrical gradients. So the polarity on this is going to be 100%. This too, same thing. I'll put it over here. Polarity again. It's got all its electrical gradients. 100%. So both of these two molecules are putting out a lot of electromagnetic signature that is attracting other molecules. And let's go ahead and examine what would happen if they actually did form a hydrogen bond. And now we have a hydrogen bond formed right here. And that makes the polarity here 75%. Now this one here has an electrical gradient right up here. Was caused when there wasn't anything opposing it here, but now there is something opposing it. Now we have another one right there. So now this electrical gradient is essentially neutralized, and now this one's polarity goes to, again, 75%. And that's the way it goes. We were to add another hydrogen bond, let's say right here. This would go to 50, this would go to 75%. And it's really just that simple. Now, of course, when we're looking at it here on a flat board, it kind of, obviously it's going to misrepresent what's actually going on in reality. In reality, it's three-dimensional, and each one of these molecules is surrounded by other molecules, and we're representing that as being surrounded by just showing these hydrogen bonds here. And actually, an H2O molecule is a tetrahedron. It's not really, it isn't circular like that. Those are all details we can deal with later. Here we have a whole bunch of hydrogen bonds. Here you'll see, and every place we see this little green here, that's where there's a hydrogen bond. And you'll see right in here, this little window here, you can write in, or I can write in the polarity. And here you get a sense of exactly how it varies depending on connectedness. The most connected of these are in the center here. This is highly connected. This is highly connected. Each one of these four have 4 hydrogen bonds, and therefore each one of these 4 has 0 polarity. See that? 0 polarity. And that's because if they had electrical gradients, and those electrical gradients are being directly opposed. In all cases, there was one here, and there was electrical gradients going across this nucleus here, and now they're opposed. Now you also notice on this that along the edges, the polarity is going to be higher, and that's simply because along the edges there's less opportunity to have a connection. So out here we see one that's 75, it's only got 1 connection. This one has 2 connections, and it's at 50%. This is at 50%, it too has 2, 50%, 50%. Here's another 75 down here. And of course, where you see 25%, well, they have 3 connections. That's 3 of the 4 electrical gradients have been contradicted. And as you'll see here, it actually does explain something that the other theory doesn't explain, and that's surface tension. Now, just imagine if all of these, instead of having the different numbers we have here, if they had 100% in there, okay? So every one of these is the same polarity, 100%. This is what the current paradigm claims to believe anyways, that if all of these had 100% polarity, we would be unable to explain surface tension. We'd also be able to explain why there's such low viscosity within the bulk of the water. So this theory actually works, which is completely different than the other theory, which completely fails because it doesn't really give us any indication of anything different from one situation to the next. Every single situation has the same polarity. So it's obviously wrong. Now, I'm not saying that makes this obviously right, but it's important to understand, though, that now that we do understand what actually causes the polarity, and that's electrical gradients that are unopposed going across nuclei. Now that we understand that, now we can understand what turns it off too, and that is the connections, which bring additional electrical gradients that turn off the polarity. So this model, the traditional model, completely fails. And it has failed ever since it was developed, right from the start. It fails, for example, to predict the very low viscosity of liquid water, because this predicts the polarity on each H2O molecule is going to be constant, it's going to be the same, and it's going to be something significant, like 100%. Well, if that was the case, there would never be a situation where H2O's viscosity was low, as we do find in the liquid phase. And it's important to understand the liquid phase is the most dense phase of H2O, and there's a reason for that, and that's because only if there's a lot of connectedness can you keep the viscosity low. Can you keep the polarity low enough to have that low viscosity? And that's what we have in liquid water. Now, with this one, it makes no difference how much connectivity you have. This one completely fails to describe anything to do with the H2O molecule. Now, to get a sense of how absurd academia can be, why don't you do this? Go on the internet, go to YouTube, type in hydrogen bonds H2O, or you could say hydrogen bonds of water, something like that. And you'll get a handful of videos, somewhere around 5 to 10 or something like that. And they will all tell you that this is how they determine the polarity of the H2O molecule. And they will completely fail to understand that the actual way to understand the H2O molecule's polarity is with respect to electrical gradients going across nucleuses that are not opposed by opposing electrical gradients. Only that really explains what we actually see in nature. Well, let's first of all point out we have 3 nuclei. 1, 2. Now there are 4 sets of electrical gradients running across nuclei here. Here creates an electrical gradient going across this. One, another one up here. So, to oppose these electrical gradients, let's say with hydrogen bonds, let's say we go ahead and we draw on really funny looking H2O molecules. Another one here, one hydrogen bond here. There's another one right here, another one right here, there's another one right here. Because of that, we now have neutralization of all of these electrical gradients. Let me show you. See this? This brings its own oppositional electrical gradient right there. On this one, brings one right there. This one up here brings one like this. And this up here brings one also. And that means that all of these get crossed out. And polarity equals 0. 0. There's 0 polarity in this because it's fully hydrogen bonded. And this is the correct understanding. The one that we've had traditionally is a wrong understanding. The people who considered that didn't really understand what they were talking about. They literally did not know what they were talking about, and they still don't know what they're talking about. And unfortunately, that's the reality of a lot of parts of science. Once they go off on a tangent, they start to dig in their heels and they stay there. Now you might wonder, well, how was it they originally got into that? I mean, how did they, when they first developed this notion of hydrogen bonding, wouldn't they have noticed right up front that their model plainly did not match up with the evidence? Well, maybe some people did, but it didn't matter because really what was going on was everyone was just confused. That's really what was going on. And when there's confusion, what do humans do? Well, they look to an expert. The expert comes up with a model, and then they start thinking of reasons to believe the model. And that's what's happened with hydrogen bonding. They came up with this model. They came up with this model which had electronegativity, and then did they actually apply it and actually start testing it and showing that, hey, you know what, this model isn't working? No, they didn't do that because they had no alternative. They had nothing else, and they wanted to believe they understood. Humans want to believe we understand. Even if we don't understand, we are more willing to believe we understand than we are to just admit that, hey, you know what? This is confusing. It doesn't make sense. Let's not adopt any position at all. Let's stay neutral. That's not the way humans are. Humans never want to stay neutral or something like that. And if you think about it, who wants to teach a course where all you have is confusion? And that's what you end up having if you taught water. And that's why they don't really teach it in colleges or high school or anything. All we know is, if you took a specialized class, you'd probably be able to find out certain things about H2O. You find out it has these anomalies. But you'd never get anywhere with the people who believe their model because they genuinely believe it. And that's what happens. People go off on tangents and they believe things, and then the group gets involved, and groups have the ability to believe the dumbest stuff ever. The dumbest stuff that's ever been believed by anyone is most likely believed by a group, because a singular individual has a hard time believing something dumb, but many individuals, when they get together, it's really easy.